Well, the next talk will be by Forrest Mozer, entitled Parallel and Altitude-Dependent Perpendicular Electric Fields Deduced from Auroral Zone Incoherent Scatter Radar Measurements.
Both as an introduction to the Chattanooga radar data that I want to present this morning and in view of last night's discussion on double layers and anomalous resistivity, I thought it would be appropriate to introduce this to begin my talk with a very brief summary of some of the parallel electric field measurements which we have been claiming to make in rockets for the past 7 years. To summarize that very quickly, on 3 rocket flights during the past 7 years into active auroral forms at times when current should have been flowing in the auroral ionosphere and ground magnetometers indicated current flows, we have with direct in situ double probes measured parallel electric fields on each of these 3 occasions. On some 4 other occasions, when either the location of the rocket in space or time or the auroral conditions would indicate that there shouldn't be a parallel electric field, that there weren't large current systems flowing. In every one of those occasions, we did not measure a parallel electric field. The properties of the parallel fields which we claim to have been measuring are interesting in view of the discussion of double layers and anomalous resistivity. It's difficult, for example, to explain our measurements, if you believe them, in terms of double layers because the altitude and longitudinal range over which we have seen the parallel electric fields are in excess of 100 kilometers. In terms of anomalous resistivity models, the parallel fields of 10 or a few tens of millivolts per meter, which we claim to have measured, would require an enhancement of the collisional conductivity, an effective enhancement of the collision frequency of a factor of about 1,000, which is very consistent with anomalous resistivity theories of a large variety of classes. The only problem with the anomalous resistivity explanation is that these measurements of tens of millivolts per meter parallel electric fields have all been made at altitudes below 500 kilometers, and it's difficult to make velocity-driven instabilities operate in the plasmas that are as dense as those present below 500 kilometers, and so that there's a problem with the explanation of that kind of data also in terms of anomalous resistivity theories. The existence and belief in this class of data that there are tens of millivolts per meter parallel electric fields at altitudes below 500 kilometers caused us to realize quite quickly that the Chattanooga radar could be used to the measurement of these parallel electric fields in the following way. The Chattanooga radar measures the perpendicular electric field as a function of altitude, and if I define the magnetic field direction as z, just to make my explanation simpler, then the Chattanooga radar measures, let's say, the x component of electric field as a function of z. And you can therefore obtain from the radar a measurement of dEx dz. And suppose you see an altitude dependence of the perpendicular electric field, therefore you measure a non-zero dEx dz, and since the curl of V is 0, this would require a non-zero dEz dx, that is to say a non-zero horizontal variation of the parallel electric field. You can combine the measurement of an altitude dependence of the perpendicular electric field with scale size arguments on the region to deduce the magnitude of the parallel electric field that would have to accompany the altitude dependent perpendicular electric field if you indeed measured such an altitude dependent perpendicular field. So armed with this kind of an idea and philosophy, we've marched up to Chattanooga on 2 occasions in the last year and a half to collect radar data, and on both occasions we indeed did see large variations of the perpendicular electric field with altitude, which causes us to infer the presence of parallel electric fields the order of 10 millivolts per meter at altitudes below 500 kilometers in Chattanooga. And I'd like to I'd like to show you the data that leads to that by showing you the first slide. This is the first night that we made, I stand out here too, first night that we made electric field measurements with the Chattanooga radar. It turned out to be August 9th, 1972, which was the middle of the Great Magnetic Storm. And this turned out also to be, from the point of view of ground magnetometer variations at Chattanooga, the most active of the nights during that very active week. What I've got in the plot, the upward top curve is the northward component of electric field. The bottom series of curves is the eastward component of electric field as a function of universal time in a time interval around midnight and spanning some 8 or 10 hours. The heavy black line is a balloon measurement of electric field, and the many lighter lines are the different altitude measurements with the Chattanooga radar of the perpendicular electric field at different altitudes up to 500 kilometers. I should point out that the scale on the eastward component of the electric field is half that of the scale on the northward component, so that full scale here is 50 millivolts per meter, and on the top curve is 100 millivolts per meter. Early in the evening, before the big magnetic bay, one sees a reasonable consistency, internal consistency in the radar data itself and in the comparison of the radar data with the balloon data. At 10 o'clock UT, a 1,000 gamma bay commenced and lasted for about 2 hours, during which time the variations in the radar data, during which, by this time, the balloon had drifted a reasonable distance to the west, so that the comparisons of the balloon data with the radar data are perhaps less significant at that time. So I'll confine my discussion then to the radar data itself. The variations in the westward component of the electric field are not inconsistent with the statistical variations that one would expect at that time. Again, keep in mind that the scale here is half the scale on the upper plot. However, in the upper plot, we see that the north-south component, or the southward component of the electric field, showed variations with altitude as great as 100 millivolts per meter. So we came back home quite excited by that result, and thinking that we had seen a variation of the perpendicular electric field with altitude, when we realized that there are other interpretations of the data that are, in my view, less plausible but not impossible, associated with the way the radar makes its measurement. The radar measures, these measurements were made with the radar by looking at 3 directions around a cone centered about the magnetic field direction. So that if you see a variation of the electric field with range gate, with distance really, some of that variation could be due to distance parallel to B, and some of the variation could be due to distance perpendicular to B, since both variations are present as a function of range gate. So we came back home and thought about that problem for a while, redesigned the experiment to make the measurements in 2 planes, as indicated in the slide. One plane magnetic east-west, another one magnetic north-south, where we'd make a series of 3 measurements, one along B, one inclined at 14 degrees to B, and one inclined at 20 degrees to B. So that if you saw a range gate dependence of the perpendicular electric field at, say, 14 degrees and 20 degrees, you could tell whether that was a variation with respect to distance perpendicular to B or parallel to B by intercomparison of the data from the different range gates. For example, if it was a variation of the perpendicular electric field with respect to distance along B, then the data in this range gate would be less than the data in that range gate, since both are pointing along the magnetic field direction. Well, in this mode of operation, then, we collected data last April, and I've inserted a slide, which is the control, which is a quiet night. Of the neutral wind, or is independent of the neutral wind. Some of the interpretation in terms of anomalous resistivity would. But one can go to Chattanooga and measure the perpendicular electric field at a lot of altitudes without knowing anything of the neutral wind. All you have to know is that you're in the collisionless regime, and then the flow velocity is E cross B.
You said that you can't tell whether the electric field is up or down, but would you remind me how you get the absolute magnitude of it when you just from DEZ dx?
From scale size arguments, that the perpendicular electric field was varying by almost 10 millivolts per meter per 100 kilometers, and so it's the southward field that's varying, so that the southward perpendicular component's varying. So that what you've measured then is that the parallel electric field is varying in a north-south direction by the order of 10 millivolts per meter, by 8 millivolts per meter in this measurement, per 100 kilometers. And now you have to stick in a scale size of how big a variation region you will allow. And the measurements are made over a spatial region that's the order of 100 kilometers, and I don't think so.
And that assumes that it's 0 at one boundary then?
Well, I don't know what it is. The parallel field could be a lot larger than the estimate you get from this order of magnitude calculation, because all you've really measured is its horizontal variation. You could have an arbitrarily big DC parallel electric field uniform in space, and you wouldn't measure it by this technique.
It seems to me that the crucial question here is the averaging, because you're doing this under very active situations, and certainly under those situations, if you look at the time history of something like a barium clouds in this kind of situation, they are twisting and turning while they're moving and things like this. So what is the averaging time here?
The data I showed has the averaging time shown in the slide. This particular data is averaged for 2 hours.
No, I mean of individual samples, individual measurements.
Oh, that depends.
I mean,
That's different for the 2 nights. During the April data, a single measurement of one line of sight velocity took 5 minutes, and during this data it took 10 minutes. So you get a vector electric field measurement roughly every 15 minutes.
Oh, there's tremendous variation in that
I
period.
agree.
So, I mean, how can you possibly deduce anything from the averages?
I think that's the point I alluded to earlier, is that all radar measurements suffer from the fact that they're making spatial averages and temporal averages over large regions of space and large regions of time, and the validity of a measurement like this is really dependent on how reproducible it is. I think to see it once makes you feel good. To see it 2 for 2 makes you feel better. If we can see it 4 more times in a row, it's likely to be there and not just to be some bad luck associated with spatial averaging. The 2 times we've seen it, we've seen the same general effect.
Forrest, this slide you have here, it looks like as you move up, the electric field rotates into the westward direction. Can I, or should I conclude from that that indicates that the westward component is produced in the magnetosphere and the southward field is produced locally?
I like to think of it that way. That's a very convenient way to remember the result, is that the southward field's a polarization field that's present in the ionosphere associated with a westward field that's magnetospheric in origin. But to me, that's a way of remembering the result rather than a proof of the validity of that statement. It's consistent with that.